So I'm back to looking at the penny lab that we did last week. In this penny lab, we had a beaker that had, towards the end, we had a beaker that had some solid copper in it. We had a little leftover zinc solid, and we decided that we were going to add some HCl, some hydrochloric acid, to this solution in order to get rid of that zinc. And so when we added the HCl, it didn't affect the copper solid. That stayed in there. And what happened to the solid zinc was we saw some bubbling occurring, and that was hydrogen gas being released. And then the solid zinc went into solution as zinc 2 plus, or as zinc chloride, which was solubilized. So the question is, why do these two reactions occur or not occur, right? Why is it the zinc solid reacts with the H plus to give zinc 2 plus and hydrogen gas, and that's a spontaneous reaction, but that the copper solid, when put in the place of H plus acid, going to copper 2 plus and hydrogen, that this reaction is not spontaneous, right? And the reason for this is because of the potential of these different metals. And by potential, we are going to be using the symbol E for that. And E is going to be measured in voltage. It turns out that if you look up the potentials of these two different reactions, you see a potential for the zinc reaction at 0.76 volts. And if you look up the potential of the copper reaction, you get a value of negative 0.34 volts. So it turns out, actually, that we can determine spontaneity with something other than just delta G. Remember, we were using delta G before, and if delta G was negative, then the reaction was going to be spontaneous. And if delta G was positive, it was not spontaneous. Now it appears that we can also look at the potential of a reaction and see if it is going to be spontaneous or not. So if potential, or E, can tell us about spontaneity, then there ought to be a relationship between delta G and E. And in fact, there is. When we take a look at this page, we see that the delta G is equal to minus NFE. And these can be standard state conditions or not standard state conditions. It doesn't matter. The N in this equation stands for the number of electrons that are transferred in this reaction. And F stands for Faraday's constant, which is equal to 96,485 joules per volt per mole of electrons. And so when I look up in the back of the book in Appendix G, what I find is that the reaction of 2H plus, excuse me, plus 2 electrons going to H2, the potential for that reaction actually is defined to be 0.00 volts, that there is no value associated with that half reaction. The half reaction of zinc going to zinc 2 plus turns out that that is a positive 0.076 volts. And when I add these two reactions together, I get the reaction of interest here, the 2H plus the zinc going to H2 plus Zn2 plus. That one happens to then be just the addition of those two potentials being added together. So 0 plus 0.76 is still 0.76. And so if I wanted to convert that potential into a delta G value, delta G is equal to minus the 2 moles of electrons times the Faraday's constant times the 0.76, and I get a value of negative 147 kilojoules. It's a negative value, delta G is negative, and so it must be a spontaneous reaction. If delta G had come out to be positive, obviously it would be not a spontaneous reaction. And if you recall taking a look at the copper half reaction, that came out to a negative 0.34 volts. So I would end up with a delta G equals minus 2 moles of electrons times 9645 times a negative 0.34 would give me a positive value and therefore not be spontaneous. By the way, I've calculated a delta G here based on the potential, but I could have also calculated it based on values from Appendix G. And if I look up all of those values in this reaction, the H plus, by the way, is 0. Solid zinc with no charge on it is also 0 kilojoules per mole. H2 is an element, so that's 0. And the only thing I have left is the zinc 2 plus. And if I were to look up that value in the back of the book, it gives me a value of minus 153.9 kilojoules. So in essence, what I've done is I found another way to calculate a delta G value. So now we've got 4 ways of calculating a delta G value. We use delta G equals delta H minus T delta S. We use delta H from delta G, delta G we can get from delta G of formation. We could get delta G from Hess's law, and now we can get delta G from these potential values that are in the book as well. Those two values should be exactly the same, minus 153.9 versus minus 147. They're a little bit different. Again, it's because of the approximation here of the potential of just being 0.76 volts. That should have been 2 sig figs, so instead of negative 147, it should probably be negative 150 kilojoules, and negative 150 kilojoules is equal to negative 153.9 if you cut it down to 2 significant figures. So delta G, again, is a state function, as we've said before.